So there's many situations can be modeled using systems of differential equation. Remember those mixing problems when we had a big tank where water comes into, or potentially water with already some solute get to mix and then goes out of the tank maybe at the same rate it came in or at a different rate. Well, what if we have a situation in which we have two tanks? And there are situations in which there could be some recirculation, or maybe it just flow on and on. Also, okay, so let's consider the situation in which we have two tanks, A and B, uh, where the solute, the salt is salt, called let X be the amount of salt in tank A, and let Y be the amount of salt in the second tank B. All right? Consider the situation where A has 50 gallons of water with 25 pounds of salt dissolved, and tank B contains 50 gallons of pure water and just pure water. Notice there's no salt in it, right? Okay, so what happens here? Liquid is pumped in and out of the tanks, on all of the tanks, right? As we can see in the diagram. Uh, now, what are you asking is so the let's recall the formula dAdt, that is to describe the rate of change of the amount of solute that changes in or out, or that changes in the container in the tank, right? So rate in minus rate out. Positive because it's coming in. Negative because it's getting out of the tank, right? We're losing some amount. So that's why the change. How do we calculate each of them? The flowing rate, which is given, times the concentration, which is given, and subtract the flow out rate times the concentration of the solid that we have, right? Okay, so now we wish to construct a mathematical model that describes the number of pounds x as a function of time and y as also a function of time of salt in tanks A and B respectively at time t. Okay, what we do here? So let's have a look at the situation. So for A, what's happening at A? A dx dt equals to, okay, what's coming in? Okay, in. Okay, pure water is coming in, right? So the flowing rate of what is coming in, which is 3 times, but what is the concentration of salt that's coming in? 0, because it's pure water, all right? What else is coming in, guys? Okay, whatever mixture from tank B, okay? Now, here is the thing. At which rate is coming in? So at 1 gallon per minute. But what about the concentration? How do we calculate concentration? We calculate the amount of a solute divided by the total volume, like in three, didn't we? I mean, we could change this to molarity if you want, but let's keep it simple as a mass per volume, if you will. All right. Okay. So, but the thing here is that x and y, they are both the variables. They change over time. So we don't know. So whatever y over the total volume, which in this case is what? 50, right? Okay. So that's what's coming in minus what's coming out. That is mixture of pure water, the other mixture, and that's coming out, right? So again, our focus is tank A, coming in, getting out. All right. Okay. So minus the rate, which is 4 times, but in this case, it's X, what we're losing, right? We're losing X, whatever that is, divided by the total volume for A. How many gallons? Also 50, isn't it? So they're both 50 gallons. Let's simplify dx dt. equals 3 times 0, which is 0. That's 1 over 50. Y minus 4 over 50, which reduces to 2 over 25, x. So that is our first equation. Number two, let's do exactly the same. Let's do exactly the same for b. So for b, dy dt, okay, dy dt would be equal to, okay, what's coming in? First of all, mixture coming from part A, isn't it? From tank A, isn't it? Which is coming in at a rate of 4 gallons per minute. But what's the concentration? Since it's coming from X, that's actually whatever X divided by 50. Are you guys with me here? Okay. Okay. Do we have anything else coming into Y? I believe we're done, right? With the inputs. Okay, let's talk about the out. So let's subtract, right? Okay, number one, what's coming out? I mean, you can write whichever you want. Okay, let me do whatever gets out of y and not recirculating back into x. Okay, so there's a rate of 3, but there's only y solute divided by 50 minus whatever goes back to x, which is at a rate of 1 times, in this case, also y divided by, what is it? 50, right? And that's pretty much the setup of the situation. Well, let me clean this up at least. Okay. So what is this? Okay. So that's dy dt equals 4 over 50, which reduces to 2 over 25 minus, be careful here. I'm not going to reduce yet. 3 minus 1, negative 3 minus 1, is that negative 4? Yes. The x, right? Thank you. Thank you. Yes. And negative 3 minus 1, negative 4, but negative 4 over 50 also reduces to negative 2 over 25. Why? And that is the system of equations, guys. So let me write it as a matrix. In matrix form, that's x, y equals to, what is that? Oh, x prime, y prime, negative 2 over 25. Be careful because the first equation has the y term first, okay? And the x term afterwards. So make sure to put them in the correct entry in the matrix. 1 over 50. And then here, another 2 over 25. And minus 2 over 25. And that times x times y. Okay, I'm not gonna solve the systems in class. I'm gonna help you set it up, set them up. I'm gonna focus only on the setup. You guys are gonna solve them for homework. You're gonna see something like this in the homework. Okay, so let's have a look at a different situation. Okay, now let's consider 3 large tanks containing brine, which is a salt solution, right? As shown in the figure below. Use the information to construct a mathematical model for the number of pounds of salt X, Y, and Z at time t in tanks A, B, and C, respectively. Okay? So, but this time, look at the system of tanks right here. There is no recirculation. It's just A going to B, going to C, and keep going. All right? Keep going. All right. So what do we do? Okay, what do we do in this case? Uh, Again, for A, I mean this looks a lot like conservation of energy, like in physics. But well, in this case, we're not talking about energy, but actually amounts going in and out of a system. So for A, what do we do? That is dx. Let's call this dx dt. Okay, call it dx dt, which is okay, what's coming in? Again, pure water, isn't it? At a rate of 4 gallons per minute times 0 because it's only pure water. There's no salt. X is the amount of salt. All right. Okay, that's coming in. All right. Oh, I forgot to write the in. Well, I think you guys can go with that, all right? Now, let me subtract because that's the only solution coming into tank one, right? Now, the next is to describe what's coming out with a negative sign. But in this case, at the same rate of 4 gallons per minute. But in this case, how about, oh, let's label X, Y, and Z for the amounts, don't we? In this case, it would be whatever X amount of salt divided by 200. Do you guys agree with this? Mass per volume, that's the concentration, X over 200. Chemistry people, I mean, for tank B, dy dt, okay? Dy dt. So, okay, what's coming into B? Okay, a mixture of at a rate of 4 gallons per minute. However, since this is coming from tank A, that contains the amount X, isn't it? So that'll be 4 times X divided by 200. Careful. Now what's coming out? Whatever we already have in Y at the same rate of 4 gallons per minute. That is 4 times, but in this case, Y over, what is it? Y over 150 this time, right? So this time we have not only a different tank system, we also have different volumes in there, right? Okay, so I believe that's it, right? That's it. So dy, well, yeah, I'll reduce shortly. Uh, for C, I'll reduce at the very end. Okay. For Z, that is the amount dz dt. Okay. Now, what's going on in tank C? In tank C, we have solution from tank B involving the variable y, the amount y. That's what's coming in at the same rate of 4 gallons per minute. But what's the concentration? That's y over the volume of B, which is 150. And then what's coming out? Whatever is coming out now is in terms of Z. That is, at the same rate of 4 gallons per minute, Z over this time is 100 gallons. All right? Okay, guys, let me reduce the equation. I should have done that from the very beginning. So this will be our x prime. Okay, let me call this x prime for short. 4 times 0 equals to 0. 4 divided by 200. Isn't that negative 150? X. What about y prime? 4 divided by 100, another 1 over 50 times x. 4 divided by 150. That's a somewhat nice number. Minus 2 times, 2 divided by 75. Y. Last but not least, z prime equals to 4 over 150, another 2 over 2 over 75, minus 4 over 100 is, which is, oh, this is y. Okay, this is y minus 1 over 25 z. Those are the equations, guys. Notice the first equation only involves x. The second equation does not include z. And the third equation does not involve x. So be careful when setting this system in the, what you call, in the matrix form. That is x prime, y prime, z prime. That is negative 150, 0, 0, x and y, that's 150, negative 2 over 75, 0, and then there is no x in the z equation, that's 0, 2 over 75, negative 1 over 25, times x, y, and z. And that is the system of equations. Well, this is a 3 by 3. We didn't do any 3 by 3s, right? But actually, you could do it, I guess, easily because it's a triangular matrix, right? It shouldn't be a big problem to get the eigenvalues for this one. All right. So let's move on to another example, and I believe that'll be the last example we do. Okay, another pretty cool application of systems of differential equations is to describe population migration. So what do we have here? A country's population consists of both urban and rural inhabitants. So within the country, well, Currently, the population is 32% urban and 68% rural. The total population does not change in this country, but people move between urban and rural areas as follows. All right. Each year, 11% of urban population migrate from the rural countryside to the rural countryside, while the other 89% stays in the urban city. Each year, 23% of the rural population migrates to the urban city, while the other 77% stays in the rural country. Okay, yes. They're asking us to let U sub t represent the proportion of the total population that is urban as a function of time in years. Similarly, let R of t to represent the proportion of the total population that is rural as also a function of time in years. All right. Write the IDP modeling the rate of change in U and R. All right. How do we go about this one? I mean, this is really another way to solve a tank problem. Well, of course, you're not going to have people in tanks, right? And you have people in the city and the rural area, but the way we're going to solve the problem is pretty much the same. So, I mean, the sense of the tanks is like the way we're gonna think for this. We're gonna think about to get the what's it called the system. So urban and rural. All right. So what are they telling us in the very beginning? There's 32% urban and 68% rural. Okay. Now, 11% of the urban population goes to the rural areas, while 23% of the rural population goes to the urban city. All right. That's all we need to know, actually. That's all we need to understand here. So see how we have like the tanks recirculating. But well, you'll see how we set this up. All right. So for dt, dt equals to okay. What? Okay. The question here is what's coming into the urban? Isn't that only people from the rural areas? Okay. But I mean, what are the numbers that we're going to substitute in there? Because we don't know the actual population. They're only telling us the percentages. So this is what we're going to do. 23 out of 100, 23%, right? 23% of the rurals. And then what's going out of the urban? Subtract. Isn't that 11% of the urban? That is minus 11 out of 100. You. All right? Are you guys following me here? Okay. So what else? Um, what about an equation for the rural population? DRDT, you know? What is this? Okay, first of all, what's coming into the rural? Isn't that 11% of the urban? Okay, 11% of the urban. Uh, what's getting out of the rural? 23%. All right. And guys, that's our system. That's it. Yeah, it looks like with the numbers reversed in a way, but that's all it is. Okay, guys, we can make a fancier study here. What if people from the urban, I don't know, they're coming from Europe? What if people to the rural are coming from South America? What if people from the rural are going to, say, China or Japan? Or what if, I don't know, people from Greenland are coming into the Europe? I don't know. We can make this even fancier. So, what's all this about? Input, whatever comes in, whatever's coming out, whatever. That's all it is. That's all it is. All right. Okay. In matrix form, U prime, R prime equals to, okay, careful. U goes first, R goes afterwards. Negative 11 over 100, 23 over 100, and then 11 over 100, negative 23 over 100. Okay. And that's the system. Oh, wait. U of zero, R of zero. They're asking us for to set up an initial value problem. All right, an IDP. That is, we need initial conditions. Well, that's related to guess what? The initial population. Where do we get the initial population from? The information here. 32% urban, 68% rural. So 32, what the hell? Okay, U of zero equals to 32 over 100 and 68 over 100. That is, as a vector, x of 0 equals to 32 over 100, 68 over 100. That's something you're going to do for homework as well, something similar. I mean, you can also model this for chemistry, guys, for for setting like sometimes some chemical reactions, A goes to B, B goes to C, etc., a chain of chemical reactions. You can set it up. A very common chemical reaction, sugar. Okay, so sugar goes to ethanol. You know what it is, right? Yeah, wine, beer, whatever. And then, well, what's next? In organic chemistry, you're going to see that ethanol, under oxidation, this is a primary alcohol, becomes acetaldehyde, right? Which is what causes hangover. So when you wake up after partying the night before, you wake up with alcohol in your body oxidized into acetaldehyde. And sometimes if the party goes like even stronger, even pretty sick, that becomes acetic acid. Oh, that looks like AI, right? Acetic acid. And well, think about maybe you've run into people who smell like acetic acid, like vinegar. That's because they party like really, really hard. So that's the change. And guess what? Whatever comes in, which is sugar, whatever comes out, which is acetaldehyde, you can set up a system of differential equations to determine the concentrations of all these chemical entities in your body as your chemistry professor. And yeah, that's what happens. All right, guys, looks like this is the end of the section, isn't it?